Okay, have you ever really truly thought about the ground right under your feet? I mean, it feels pretty solid, right? Permanent, even. But the truth is, our planet is anything but still. It is constantly moving, constantly being reshaped by these incredible forces from deep within. So today, we're going to dig in and uncover the powerful geological processes that are literally sculpting our world as we speak. So let me just ask you this straight up. The ground you're on right now, does it feel totally solid, stable, like it's not going anywhere? I'm guessing for pretty much all of us, the answer is a big yes. But as it turns out, that feeling is not the whole story, not by a long shot. Yeah, the wild truth is the ground beneath us isn't one solid piece at all. It's much more like a gigantic jigsaw puzzle. Our planet's entire surface is made up of these enormous, rigid pieces that are in a constant, and I mean incredibly slow, state of motion. So, okay, if our planet is this moving puzzle, then what exactly are the pieces? To really get what's going on with this whole geological story, we need to meet the main players. And here they are. These giant puzzle pieces are called tectonic plates. The entire outer shell of our planet, this layer we call the lithosphere, is fractured into these massive plates. And get this, it's not just the continents. The land we live on and the huge ocean floors are all just parts of these gigantic moving slabs of rock. But of course, that just brings up an even bigger question, right? Why do they move? I mean, what kind of force is powerful enough to shove entire continents around? To find that answer, we've got to take a little journey deep inside the Earth. We're talking from the crust all the way down to the very core. All right, so our journey starts right here, on the surface, with the lithosphere. This is that cold, brittle outer shell of the planet. A really good way to think about it is like the cracked shell of an egg. This solid, rigid layer is the part that's broken up into all those tectonic plates we were just talking about. Now, right underneath that rigid shell is the key to this entire mystery, the asthenosphere. Our source material has a perfect description for it. It's like taffy. Now, it's still solid rock, but it's so incredibly hot that it gets, well, pliable. It can actually flow just really, really slowly. This gooey, flowing layer is what allows those hard, rigid plates of the lithosphere to just kind of glide around on top of it. Going deeper still, we hit the mantle. This layer is an absolute beast. It's by far the Earth's thickest layer and makes up most of our planet's total bulk. It's this super hot, dense layer of rock that's almost entirely solid. But it's in here that you find those pockets of magma, the molten rock that ends up fueling volcanoes. Next up, we arrive at the outer core, and here, things get wild. It is so unbelievably hot down here that the iron and nickel aren't solid at all. They're a swirling, churning ocean of liquid metal. And all that churning has a super important job. It's what generates Earth's protective magnetic field. Pretty cool, huh? And here we are. We've made it to the very center of our planet, the inner core. Now check this out, because here's a total paradox for you. It's actually even hotter here than in the liquid outer core, so you'd think it would be molten too, right? Nope. The pressure from the weight of the entire planet pressing down on it is so intense that it forces the iron and nickel atoms to lock together in a solid state. Mind-blowing. So if we look back at our whole journey, you start to see a really clear pattern. As we travel deeper and deeper toward the core, from the lithosphere all the way to the inner core, each layer gets way denser than the one above it. And this whole increasing density thing, it is absolutely crucial for what happens next. Okay, so we've seen all the layers, we've seen the taffy that the plates float on, but what's actually the engine driving all of this? Well, the power source for all this movement is the planet's own mind-boggling internal heat. Let's just ask the big question directly. We've got these massive, continent-sized plates floating on this taffy-like layer. What in the world is the force that's strong enough to push them all around the globe? The answer is a process called convection, and it's all powered by that crazy heat coming from the Earth's core. The best way to picture it is like a pot of water boiling, but in super, super slow motion. Rock deep down in the mantle gets heated up by the core, which makes it less dense, so it slowly starts to rise. Then, as it gets near the surface, it cools off, gets denser again, and sinks back down. This creates these huge circular currents, kind of like a giant conveyor belt, and that's what drags the tectonic plates along for the ride.
So you've got this giant, slow-motion conveyor belt dragging these massive plates all over the globe. Well, what happens when they inevitably bump into each other? All the action, all the drama happens at the boundaries where these plates meet.
And they interact in a few different ways. So at what's called a convergent boundary, you have two plates moving towards each other. This results in these massive collisions that can literally build mountain ranges. Then you have divergent boundaries, where they're doing the exact opposite. They're pulling apart, which creates a gap that allows new material from the mantle to rise up and form new crust.
And then there's a third major type, the transform boundary. Here, the plates aren't smashing into each other head-on or pulling apart. Instead, they're just sliding and grinding past each other sideways. This is the kind of boundary that's famous for building up enormous amounts of stress that can eventually get released as a massive earthquake.
So, when you put it all together, the heat engine deep inside, the slow-motion convection currents, the grinding and colliding plates, it all points to one inescapable conclusion. We live on a planet that is in constant, dynamic, incredible motion. The source material just says it perfectly. These plates move constantly, but slowly, on top of a layer of Earth called the asthenosphere. And yeah, that movement is way, way too slow for us to feel day to day. But over millions of years, it completely changes the face of our world. And that leaves us with one last really powerful thought. The world map that we all know so well, it feels permanent, doesn't it? But it's really just a geological snapshot in time. Every single process we've just talked about is still happening right now, deep beneath our feet. So the real question is, if the continents never stop moving, what will our world even look like 100 million years from now?